Dun, 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 dun. Time for section 6.4, Sine Law. So the gist of what we're going to do today is pretty simple. We're going to be looking at how you can solve triangles that aren't right angle triangles. Now you'll notice one thing here. I've got my calculator and this thing is blinking. It is degree mode that you must be in. Make sure your calculator is in degree mode. That's the very first thing you should be doing. Okay, so once you've got your thing in degree mode, you're ready to get going here. And okay, calculator, we're good. Okay, there we go. So just a quick little check, because what I managed to do before is I managed to actually not have my calculator in degree mode. So if you go sine 90 equals 1, that's good, because that's something we should know. Okay, so sine law. So the idea is real simple. We're going to start with a triangle, and we're going to derive sine law just by working out some basic things. So if we have a scalene triangle, scaling just means there's nothing special about it, just a randomly drawn triangle. It's not equilateral or isosceles. We can label the sides with lowercase letters, A, B, C, and then those sides are opposite to angles capital A, capital B, and capital C. So the picture here basically explains it all. One tiny thing I'll mention is that sometimes side lengths aren't just little b. Your textbook sometimes likes to say if you have a side connecting vertices A to C, we could call it AC. So that is something also known as AKA. So just be aware of that. I like to use the lowercase letters, but sometimes you'll find that uppercase letters are used. Okay, so the way we can derive sine law is very simple. We're going to solve for the height of this triangle in two different ways. So what we do is we're going to draw the height here. Okay, so we're going to just make a perpendicular side, imaginary side here, which is going to be the height of the triangle. Now the reason I do this is because I have formed two right angle triangles. Here's one of them here, terribly drawn, and then here's the other right angle triangle here. When I have right angle trigonometry, I can use SOHCAHTOA. I can't use SOHCAHTOA on a non-right angle triangle. So by drawing that height, I can now say sine of capital A equals opposite over hypotenuse. So the opposite side to angle A is the height, and the hypotenuse is side C up here. I can also write sine of capital C from this point of view. Its opposite is H, and its hypotenuse is A. So I can write sine C equals H over A. What I can do then is I can multiply both sides by C on the left equation here, and I can multiply both sides by A over here. And because C sine A is equal to H and A sine C is equal to H, my OCD is bothering me there, let's just write that H a little better. Now I can say that C sine A equals A sine C. And if I want, I can go one step further and I can get this equation so that I've got all the same letters on the same side. So I can divide both sides by A, and I can divide both sides by C, and I can get sine A over A equals sine C over C. And what I have here is I actually have a nice little relationship. This is actually a simplified version of sine law. So what I can do is I can now use pairings of angles and their opposite sides to figure out other pairings of angles and their opposite sides. So this is all about opposite pairs here. So what sine law is really useful for is if I know opposite pairs of angles and sides, I can solve for any other opposite pair of angles and sides. So pretty handy. Now the way I derived this, I wound up getting sine A over A equals sine C over C. If you drew your triangle a little differently, like your height went across like that, or your height went across like that, you would actually derive a similar formula where you'd have sine A over A equals sine C over C. And, oh, that's the one I just did. I mean sine A over A. Sine A over A equals sine B over B. This is the tongue twister. And you could wind up with sine B over B equals sine C over C. So you can actually end up with all three possibilities. And when we put it all together here, I'll just give you the result rather than showing you all the different ways you could do it. The result is this. This is sine law here on the left, where you have sine A over A is the same as sine B over B is the same as sine C over C. And if you flip the whole thing around, you can do that. You can take the reciprocal to get this guy over here. So that's sine law. It's handy. We don't ever have to actually know the height of the triangle. That was just something we used to derive it, and this is the result. So what we can do is we can use this to determine the length of an unknown side x. So what we would normally do is we'd approach a triangle like this. Okay, we can see we've got a couple angles, a side angle pairing over here. What we would do is we'd start by labeling it. So you can label it any way you want. If you want to start with A up top, B down here, and C over here, that's fine. What that would mean is that this side over here is opposite to angle C, so it gets called a little c. Opposite from side B is, angle B is side B, and then opposite from angle A is side A. So that would be all the way down here. Anyway, you don't need to draw those arrows. Okay, so to use sine law effectively, we have to have a known side angle pair and an unknown side angle pair. So by that I mean, if I have side C here, I really need to know angle C, because what I have is I have a known angle B, but I have an unknown side B. So I do have to do a little tiny bit of work before I can use sine law. Also, it's worth mentioning, yeah, I know angle A, but I don't care about side A, so that's not something worth figuring out at all. Okay, so the way I would need to solve for this is I need to figure out what the heck this angle is in here, because I need to have the known pair of C and C. So what I can do is I know that all triangles have three angles that add up to 180. So what I would do is I'd go 180 minus 39 minus 58. I don't know why I put a little dot in there, whatever. And I get an angle of, now see my calculator has gone and turned itself off. Is it going to turn itself back on? Okay, there we go. So what I can do is I go 180 and then I subtract from it 39 and then I subtract 58 equals, okay, so I get an 83-degree angle. Once I know that, I now have a known pairing, so I would say sine of C over little c. And I would like to know side B, so I have to write sine capital B over little b. I don't care about sine A over A, so I'm not going to include it. I know the sine law had all three of them, but you always just take 2/3 of it. So whenever you're doing sine law, you just need to use like 2 of the 3 parts. Okay, so the way I'm going to solve for this is I'm going to write this as sine. So angle C is 83 degrees. This is 14.7 centimeters. This is 58, and then this one here is B. Okay, so I have the variable I need to solve. In fact, I'm not going to write B, I'm going to write X, because that's kind of the actual variable I'm trying to solve for. So what I need to do here is I need to get the variable x out from wherever it is. So I'm going to multiply both sides. I'm going to do this the proper way, and then I can start to do like little sort of cheaty math hack sort of ways. The proper way is to multiply both sides by x, which is going to cancel these out. And then what I'm going to do is I'm going to multiply, I can do this in the same step or a different step. I'm going to do it in the same step just to save writing. I'm going to multiply both sides by 14.7 divided by sine of 83. So I'm going to multiply both sides by 14.7 divided by sine of 83. Okay, so the 14.7 on the bottom cancels with that one. The sine 83 on top cancels with that one. And if you're good, you don't even have to be that good. You just have to be a little bit organized. You can see what's left on the right. You've got sine of 58. You're multiplying it by 14.7, and you can extend that whole division line if you like under the entire thing, and you'd have sine 83 on the bottom. So this is super important. Make sure your calculator is in degree mode, which it is. So we're going to write sine of 58, and then we're going to multiply that by 14.7. Then divide by sine of 83. Okay, so we get an answer that says x equals 12.55999, whatever, okay. So basically we'll round this to something reasonable. I think 12.6 is reasonable given that we've got 14.7 over there. So then you do a little bit of a check. Now, full disclosure, I did this example once before where I did not put my calculator in degree mode. I put it in radian mode. I got something like 15, which seemed reasonable. But the reason why I was starting to worry is because when you look at this, I know this isn't a right angle triangle, but this is an 83-degree angle. It's kind of close, which means that the side opposite to it, C, should probably be the longest side. So 14.7 should be the longest side, so getting an unknown side of 12.6 sounds right. When I got 15 before, it didn't sound right. And just a general thing for triangles, I mean, it's pretty common sense, but the smallest sides are opposite the smallest angles. If I did the work to figure out what side A is, I can guarantee you it would be smaller than 12.6. Okay. Determine the missing angle theta. So in this case, what we have is we've got, what do we have? Let's see. So we can see here we've got an angle and we've got a side. So we've got an angle side pair, which is fantastic. And if we want to figure out this, we need to know what side it's across from, or we need to figure out what this missing angle up there is, and then we could use that. So there's a couple ways you could do this. The easiest way in my mind would be to figure out this angle up here, and I'm going to call this x. And if we know that, then we can easily work out what the angle is. So again, we're going to label this any three letters you want. A, B, C are common. It doesn't have to be. I'm going to call this B, C. So I'm actually going to just leave that as B. I'm not going to assign a variable to it because capital B will be the variable. Okay, this is side C, this is side a little b, and this is side a little a. If you found the last example to make perfect sense, you might want to take a sec, stop, and try this one yourself. Otherwise, I'll just keep on going with it. So what do we do here? We know that we have a and a little a, so I'm going to write sine of capital A over sine of little a, and I would really like to know what angle B is, so I'm going to write sine of capital B over little b. Once I have that, I can get all my information and I can go ahead and do it. So here's the calculation. I'm not going to explain too much other than I'm just going to get her done. This one's pretty easy to solve actually. You can multiply both sides by 12 right away. And we'll go ahead and we'll get 12 sine 45 over 9 equals sine of b. And if you want to be extra fancy, you can say b equals, and then you'd inverse sine this entire thing. So we'd actually inverse sine this entire expression here. You can work it out as a number if you like, but I kind of like doing it like this. So what we do is we go inverse sine. So on our calculator over here, we're going to go inverse sine. We're going to use brackets because we're going to inverse sine the entire thing. This can be sine of 45. I always like to close up that bracket. Divide by 9 and make sure you close this bracket to inverse sine the entire thing. When you do that, you're going to get B equals 70.52 or whatever. I'm just going to write it as 70.5 degrees. Now, I don't necessarily guarantee that this triangle is drawn to scale, but if this seems reasonable that it's a 70.5 degree angle, good. Now, of course, I just have to figure out theta here. So theta, or angle C, but it's labeled theta in the drawing. So theta would be 180 minus 45 minus 70.528, blah, 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 blah. Okay, so we just go 180 on our calculator, go up to our calculator here, we go 180, we go minus 45, and then instead of subtracting 70.5, I'm actually going to subtract. I'm going to use my answer key here to make sure I get the exact value. So the exact value here is 64.47, blah, blah, blah. Okay, so I'm going to round that to 64.5 degrees, and there's my angle. Okay, now there's one more thing here, it's obtuse angles. So what we have to also keep in mind here, we'll see sine law can be a little tricky at times. Sine law works for obtuse angles, but you got to remember that if you're ever solving for an obtuse angle, that when you push sine to the -1, you push that second function sine or inverse sine or even arc sine, they all mean the same thing. This gives a reference angle only. So in the last example, I actually did inverse sine and I got 70 degrees. That was the reference angle. What's tricky about sine sometimes is that what I could have been solving for is 180 minus the reference angle, which would be about 110. And you don't actually super duper know. So when we are dealing with obtuse angles, and obtuse means greater than 90, and remember acute is less than 90, what we have to do is you have to remember the supplementary angle. I don't know if you've learned about that before. That used to be in grade school geometry. I don't know if they've taken it out or not, but anyway, if the angle is obtuse, we're always going to go 180 minus the reference angle. So just a quick little explanation here. When you have an angle, like let's say you have a triangle here, and I know we said we're getting away from the terminal arm kind of stuff, but we got to remember that this is actually kind of the same situation here. If we have an angle and we use sine law and we solve for it, what we don't know necessarily is we don't know if we're getting this angle or if we're getting this angle over here. That's kind of the whole point. So we could get an angle of, let's say in the last example we had 70 degrees, but if you inverse sine an angle in quadrant 2, you'll get the same reference angle 70 degrees, but it's actually 110. So do keep in mind that when we're working out these triangles, there still is this connection to the 4 quadrants. All students take calculus business. Okay, so anyway, let's see this example. So now in this triangle, H is obviously obtuse, so we know it's obtuse. If you're wondering, what if we don't have a diagram? That's a whole other kettle of fish, and that's actually going to be our next lesson. But right now, we're just going to stick with this. So we can see H is clearly obtuse. It's greater than 90 degrees. So let's see how this would get solved for if we were actually using sine law. So now this is angle H. So let's not call it ABC. Let's go with like HIJ or something. That makes this side opposite from H, little h. That makes this side little I, and that makes this side all the way over here, little j, okay? So what we're going to do is we want angle H, so we're definitely going to have to write sine of H over little h. And we have a I, side I and angle I pair. And no one cares about j and little j. Okay, so the way we're going to do this is we're going to write sine of H equals side H is 11.9. This is sine of, let's see, 52. And then this would be side of 10. So solving this is pretty easy. I'm not going to show all the work here. I'm just going to multiply both sides by 11.9, and I'm going to inverse sine. So I'm going to go 11.9 times sine of 52. And it's over 10, and then I inverse sine. So I'm just doing all my steps together as one. And if you like to do that, that's perfectly acceptable. So we go to our calculator, we go inverse sine, and we go 11.9, and we go, you don't even have to write multiply sine 52, you can just write sine 52, at least on my calculator. And then we divide by 10, and we get ourselves 69.67. So here's the thing. So we just calculated 69 point, let's just say 7 here. Does this look like a 69-degree angle? And the answer is absolutely not. It's definitely bigger than 90 degrees. So what we would do is we would say, therefore, since H is clearly greater than 90 degrees, H equals 180 minus 69.7. And then we get, well, let's go to our trusty calculator here to make sure we get a precise 180 minus the answer. And then we get ourselves 110.3. 110.3 degrees. And that looks more like the angle. So sine is a little tricky for that reason. Sine is the only angle, the only trig ratio where if you solve for a 69-degree reference angle, it could be here or here, which means the angle could be 69, or it could be, 110 point whatever. You don't have the same issue with tan, and you don't have the same issue with cosine, because if you have some quantity and you're going inverse cosine, it's only positive in quadrants 1 and 4, and that means your angles are like, let's say like, I've been saying like 70. The other angle would have to be 3 360 minus 70, right? So 290. And then you go, well, 290 doesn't work in a triangle, right? And tan's the same thing. Tan would only be positive in quadrants 1 and 3. So if you had a 70-degree angle here, then your full would be, let's see, 180 plus 70. So this would be 250. And again, no triangles contain a 250-degree angle. But because sine is positive in quadrants 1 and 2, and here's 0 and here's 180, that means you have two possibilities for how to interpret the calculation of sine, and they're both realistic and they could both exist in triangles. Okay, so that's sort of like part one here. I mentioned what do we do when we don't know exactly if h is greater than 90 or less than 90, because if I did not give you this drawing, if I just described it, you'd have a whole other issue. So that's a whole another case, and we'll look at that next time. So this is part one. Part two is coming up pretty soon.